So when we last left off, we were discussing Lewis structures and molecular shape. Now, what we're going to do this class session is connect the idea of molecular shape to broader properties such as molecular polarity, which has an important role in determining melting point, boiling point, and other very important physical properties. So, as a refresher, to help us understand the nature of molecular polarity, we need to first understand bond polarity. So we discussed in earlier lectures this idea of a chemical bonding continuum, where if we look at delta En, which is the difference in electronegativity between two atoms, depending on the difference in electronegativity between atoms, we have either a pure covalent bond, otherwise known as a non-polar covalent bond. When we have a difference in electronegativity that's substantial but not greater than 2.0, we have what's known as a polar covalent bond, where our electrons are shared unequally. This polar covalent bond is indicated using a dipole, which indicates regions that are electron rich and electron poor in our molecule. In general, bonds are more polar, and as a result, they have more quote-unquote ionic character, the greater the difference in electronegativity between atoms in a bond. Just a refresher for those who are asking to themselves, what is electronegativity again? As we discussed previously, electronegativity is a measure of how readily an atom attracts electron density in a chemical bond. In general, electronegativity increases moving up and to the right on the periodic table, with fluorine being the king of electronegativity. Do these concepts look familiar to everyone? We actually talked about them in this chapter earlier on.
Yes.
Okay, perfect. So, with that established, with that set up, let's now take this idea of bond polarity and apply it to molecular polarity. So, molecular polarity is the net polarity of your molecule. So, type 1 molecular polarity is based on relative electronegativity. So we draw our individual bond polarities as arrows, and then we use what's known as vector analysis to add our bond dipoles and estimate our net dipole. If there is a net dipole, the molecule is polar. So looking at a very simple example, in hydrochloric acid, otherwise known as HCl, we have a polar bond, right? Chlorine's more electronegative than hydrogen. So chlorine will pull electron density towards itself. Since our molecule has just one bond and the bond dipole is pointing towards chlorine, there is a net bond dipole, and as a result, there is a net molecular dipole. Now, this gets a little bit more complicated when we have multiple polar bonds. So, one trick that we can use is dipoles can be treated as vectors, which are a quantity with a magnitude and a direction. And we can add our dipoles together by adding their x, y, and z components. It's simpler than it sounds because there's a trick for adding vectors that makes things a lot easier. Well, if you try to look at different polar and nonpolar molecules, you'll begin to notice a trend. First, our dipoles cancel only if the bonds are symmetrically arranged and have the same electronegativity, if we're bonded to atoms of the same element. So since the molecular dipole is the sum of all of our bond dipoles, symmetrical arrangements of polar bonds with the same electronegativity difference lead to net nonpolar molecules. So you can have molecules with polar bonds that are nonpolar. Let's look at carbon dioxide for a moment. So as we can see, we have two polar bonds, but those polar bonds are arranged symmetrically. The dipoles have the same magnitude, we have the same bond dipole, but they're pointing in opposite direction. As a result, our dipoles cancel. Does that make sense to everyone? This idea that you can have polar bonds, but if they're arranged symmetrically, and if your central atom is bonded to exactly the same atoms arranged symmetrically, you have no net dipole. Does that idea make sense to everyone? So there's a shortcut that you can use. So the molecular polarity shortcut that I like to invoke, a molecule is non-polar, so not polar, has no net dipole if both of these conditions are met. First, either all atoms bonded to the central atom are identical, or the difference in electronegativity between atoms bonded to the central atom and the central atom is less than 0.4. That's our first set of conditions. So this is the first condition. The second condition is that the central atom must have no lone pairs, or it must have a symmetrical geometry, where a symmetrical geometry is the linear, trigonal planar, tetrahedral, and square planar geometries. If either of these conditions are not satisfied, otherwise the molecule will be polar. So let's apply this idea and let's look at a sample molecule, such as water. So looking at water, does water have polar bonds? Does water have polar bonds? Let's run through our criteria. Do we have polar bonds? Do we have bonds with a difference in electronegativity? Yes or no? Do we have polar bonds in water? Yes. The oxygen-hydrogen bond, there's a clear difference in electronegativity. So looking at water, we have polar bonds. Okay. Okay, and second, do we have a lone pair on our central atom? Do we have lone pairs on our central atom? Yes, so we have lone pairs. And as a result, the dipoles do not cancel. So if we look at the general direction of both of our bond dipoles, we can see and add them together and get our net dipole. And as we can see, water has a net dipole, so water is polar. Does that make sense? So if your bond dipoles are not arranged symmetrically, and if your central atom has a lone pair, your molecule will likely be polar. So let's look at an example. I'll do these first two as they're pretty interesting representative examples. So we're asked to draw the Lewis structure and overall molecular dipole. You always need to keep in mind that geometry directly impacts molecular polarity. So if you look at hydrofluoric acid, or HF, HF looks like this. And we definitely have a polar bond. Looking at all of our bond dipoles, if we add them up, we get our net molecular dipole. So as we can see, hydrofluoric acid is polar. Let's look at another example. Let's look at carbon tetrachloride. So carbon tetrachloride, as we've seen in our earlier Lewis structure examples, looks something like this. Now, we certainly have polar bonds, right? Chlorine's more electronegative. So we have 4 polar bonds, okay? So making our notes, we do have polar bonds. And we have the same atom bonded to our central atom. Okay. Do we have a lone pair on our central atom? Do we have a lone pair on our central atom? So we have no lone pair. And as a result, we have a symmetrical geometry. As a consequence of this, as both of these conditions are met for our shortcut, we have a non-polar molecule. So even though we have bond dipoles, because of the way that those bond dipoles are arranged in 3D space, the net dipoles end up canceling out. So we have no net dipole. All these dipoles cancel out, and we have a non-polar molecule. We only care about our central atom because our central atom controls the geometry, controls how these dipoles are arranged in 3D space. And we look at our bond dipoles to understand and get a sense of how we look at our central atom to figure out our bond dipoles, how our bond dipoles are arranged in 3D space, because those bond dipoles will tell us when we add them all together, what is our molecular dipole. Does that make sense? Perfect. Any questions on this example?
Professor, how do we know chlorine is polar? How do you decide it's polar or not?
So if we look at our electronegativity table, so we know electronegativity increases going up and to the right, right? So since chlorine is farther to the right than carbon, if you look at the table, chlorine should have electronegativity value of around 3.0, while carbon has a value of around 2.5. You don't need to memorize the numbers, but we clearly see that chlorine is farther to the right on the periodic table, and as a result, it's more electronegative. Because chlorine's more electronegative, if we look at a carbon-chlorine bond, our dipole will point towards our more electronegative atom, as it draws electron density towards itself in a chemical bond. Does that make sense?
So if chlorine is, let's say if chlorine is 2.8, but because difference is 0.3, then they're no polar, right?
Yes. And in general, you only see non-polar bonds if it's the same atom or if it's a carbon-hydrogen bond. Most other bonds have a difference in electronegativity greater than around 0.4.
Okay, thank you.
Any other questions that I can address? If not, let's keep going and let's try to work on drawing the Lewis structure and overall molecular dipole for the following molecules. I'll do the first one and then you can work on this second example. So C2H2. So for carbon, we have 4 electrons and we have 2 carbons. That gives us 8 electrons. For hydrogen, we have 1 electron and we have 2 hydrogens. Adding it together, we have 10 electrons. We put each of our carbons in the center and we surround it with our hydrogens. Then we form 1 bond each. That gives us a total of 4 electrons remaining. we place our lone pairs on carbon, and to fulfill the octet rule, we take each of our lone pairs and we move them down to form a triple bond. Now, this example is really important because it highlights how we consider bond dipoles and molecular polarity. So first, let's think about do we have any polar bonds? Do we have any polar bonds in our molecule? Well, if we think about a carbon-hydrogen bond, the difference in electronegativity is less than 0.4, and a carbon-carbon bond, the difference in electronegativity is certainly going to be less than 0.4. So we don't really have any polar bonds or substantially polar bonds in this molecule. And the second thing that we notice is that we have a linear geometry that is symmetrical. So even if we draw out our theoretical dipoles, right? As we notice, are our bond dipoles pointing in the same or opposite directions? So looking at our dipoles, are they pointing in the same or opposite direction? Opposite. So even if we did have a dipole, our dipoles cancel out. So this molecule would be net nonpolar. The difference in electronegativity is found looking at the electronegativity table and reading off the electronegativity values for carbon and hydrogen. In general, carbon-hydrogen bonds are considered nonpolar as they have a very small difference in electronegativity. So,
Professor, are the arrows going that way because they're pointing towards the more electronegative atom, like carbon has more electronegativity
yes.
than hydrogen? Okay.
Yes, exactly right. And we look at the arrangement of these bond dipoles in 3D space, and we look at how each of our bond dipoles are arranged, and when we add them together, if the dipoles cancel, we have a nonpolar molecule. In general, if you only have carbon-carbon and carbon-hydrogen bonds, your molecule will almost always be nonpolar. Does that make sense? Any other questions on this example? So let's have you work on an example now. I'd like you to draw a Lewis structure for ammonia, and I'd like you to tell me whether it's polar or non-polar. This example is about of the same difficulty that you'd see on an exam or quiz. So you should be comfortable doing this ammonia example. So I'll give everyone about 3 to 4 minutes to try and draw out the Lewis structure. And then from there, we can focus on indicating whether this molecule is polar or non-polar. So we have a tentative assignment that this molecule is polar. Let's keep working on this example, and don't be shy to share your own Lewis structure drawing for this molecule and your own assignment for whether this molecule is polar or non-polar. And really focus not just, is it polar or non-polar, but why? What is the basis for your conclusion?
So the first, like just going through the 1, 2 down the line for
Yep.
polar bonds, would we be looking at which has more electronegativity? And in this case, it would be nitrogen.
Yep, and you look at it for each bond. What
Okay.
do we have a bond dipole? Do we have a difference in electronegativity?
Okay, gotcha.
Does that make sense?
Yes.
Perfect. And the explanations I see in the chat look great. Let's give everyone about another minute to compose their proposal, and then we'll discuss this example. Just to make sure everyone has enough time.
Professor, you said it has to satisfy the both condition, right?
Yep.
So as soon as we see the central atom has lone pairs, it means it's polar, right?
In most cases, and in all the cases you'll see in this class, yes.
Okay,
Yes.
thank you.
So let's discuss this example now. So first and foremost, so let's write out the Lewis structure for ammonia. So nitrogen contributes 5 electrons, hydrogen contributes 1, and we have 3 hydrogens. That gives us 8 electrons. We put nitrogen in the center, we surround it with 3 hydrogens and form 1 bond each. We have 2 electrons remaining. Our lone pair goes on nitrogen to complete its octet. Now, as we notice, to think about whether or not we have polar bonds, we do have polar bonds. Nitrogen is more electronegative, and all of our bond dipoles are pointing towards nitrogen. Okay, so we have polar bonds and we have the same atom, but as we notice, we have a lone pair. So we have a lone pair and we have polar bonds. And as a result, if we look at all of our dipoles are pointing up. And if we add our dipoles together, we get a net molecular dipole. So in turn, that means this molecule is polar. Does that make sense to everyone? Does that make sense to everyone? Any questions on this example? Okay, let's look at some really important observations on this idea. So since the molecular dipole is the sum of all dipoles accounting for bond direction and bond dipole strength, adding more polar bonds does not necessarily mean you get a more polar molecule. The geometry really is key. Depending on the bond polarity and the geometry, you will get a different dipole strength. So this is part of why we focus a lot on the geometry. Lone pairs affect our geometry and affect how our bond dipoles are arranged in 3D space. Okay, so now we're going to switch gears a little bit and we're going to focus on this next topic, which is we're now moving into ionic compounds and discussing and naming and writing the formulas for ionic compounds. So to start us off, we're going to need to discuss polyatomic ions. Polyatomic ions are charged molecules, ions in other words, containing 2 or more atoms covalently bonded. So I provided you a table of polyatomic ions, and you're responsible for memorizing all of the polyatomic ions in the first part of this table. You need to know their name, formula, and charge. This will be important because many of the compounds that we're going to discuss in this class contain polyatomic ions. And you need to understand the formulas and charge of different polyatomic ions in order to appropriately name compounds and appropriately write the formulas for compounds. Does that make sense to everyone? Okay, so before we move on, we should talk about some tricks for memorizing polyatomic ion names, as there's a system for naming polyatomic ions using prefixes and suffixes. So the per-8 form indicates the ion with the most oxygen atoms. In other words, it indicates the ion with about 1 more oxygen atom than the 8 ion. So for example, perchlorate has the formula ClO4-, while chlorate has the formula ClO3-. You're going to really want to memorize the 8 ion. This is the starting point that different prefixes and suffixes modify to get new formulas. So the per-8 ion has the most oxygen atoms, or 1 more oxygen atom than the 8 form. So if you memorize the 8 form, it allows you to easily write the formula for the per-8 ion. Does this idea make sense? Does everyone see how we go from 8 to per-8? We've picked up an oxygen. So the 8 form is the ion with the second most oxygen atoms. It is easiest to memorize the 8 ion for each set of polyatomic ions. So for example, PO4 3- is known as phosphate. NO3- is known as nitrate. SO4 2- is known as sulfate. ClO3- is known as chlorate. The reason why I'm showing you these different formulas is that the 8, ite, and per-8, the prefixes and suffixes, do not indicate an absolute number of oxygen atoms. These prefixes and suffixes indicate a relative number of oxygen atoms for that ion. So you memorize the common 8 forms, and then when you change the prefix and suffix, you change the formula appropriately. So for example, we can go from chlorate to perchlorate by just adding an oxygen. Makes it easier to memorize rather than treating these as separate ideas. The next common form is the ite form of our ion. It's the ion with 1 less oxygen atom than the 8 ion. So for example, NO3- is known as nitrate. If we lose an oxygen atom, we get NO2-, which is nitrite. 8 to ite, we lose an oxygen atom. Likewise, SO4 2- is known as sulfate. SO3 2- is known as sulfite. Does this make sense to everyone? Any questions on these nomenclature rules? The next form that we have to consider is the hypoite form. It's the ion with the least number of oxygen atoms, or the ion with 2 less oxygen atoms than the 8 form. So for example, if ClO3- is known as chlorate, if we lose 2 oxygen atoms, ClO- is known as hypochlorite. So this really provides you a system for organizing and memorizing the polyatomic ions rather than memorizing them individually. You're welcome to use any method that you prefer. You just need to be familiar with all of these polyatomic ion names, formulas, and charges. Yep, exactly. If we lose 1 oxygen from the 8 form, we generate the ite ion. If we lose 2 oxygens, we generate the hypoite ion. Any other questions on this format for memorizing polyatomic ion names and formulas? Any other questions that I can address?
Professor, can you say that again? You said if we lose 1 oxygen, it's, what was that?
So let's start from the top. So you memorize the 8 form. If we gain an oxygen, it's the per 8. If we lose an oxygen from the 8 form, we generate the ite ion. If we lose 2 oxygens from the 8 form, we generate the hypoite form. Does that make sense?
Yes, thank you.
Perfect. Any other questions? If not, let's keep going now. And let's talk a little bit about chemical formulas once again. This is a review, but chemical formulas specify the number of atoms of each element in a molecule or compound. And the subscript indicates the number of atoms of that element. So this subscript of 3 tells us we have 1 cobalt and 3 chlorines. Subscripts can also indicate the number of polyatomic subunits or ions. So in this case, we have 3 calciums and we have 2 phosphates, which are PO4 3-. We'll talk about where I got the charge momentarily. So I'll do a sample example and then you'll do the next set of review examples. So looking at copper cyanide, I see I have 1 copper, and note the 3, this subscript applies to everything in the parentheses. So I have 3 carbons and 3 nitrogens. For sodium hydrogen phosphite, I see I have 2 sodiums, 1 hydrogen, 1 phosphorus, and 3 oxygen. Does this make sense? Does this look familiar to everyone? You're going to need to be really careful analyzing the formulas of different compounds in order to progress and name compounds efficiently. Does this example make sense? Okay, so I'd like everyone to take a moment and look at example A and B, and I'd like you to indicate the atoms of each element in A or B. And as a bonus to this, if you want, you can try naming each polyatomic ion that you notice in each of these molecules. The bonus question is just in case you finish your atom count early, you can sort of get used to recognizing and noticing common polyatomic ions in your formula. So let's spend about 3 to 4 minutes on this example, and then we'll come together as a group to discuss. So don't be shy to indicate the number of atoms of each element in compounds A and B. And as a bonus, you can try to identify the polyatomic ions. And try to break down the formula into the number of individual atoms of each element. We're already starting to see some reasonable responses in the chat. If you have your atom counts done, you can focus on naming and identifying the polyatomic ions in each of these structures. And we'll discuss this example in about another 2 minutes. It's okay. The name, focus on the individual ions, just recognizing their formulas and names. And we'll talk about that. This is just a bonus and a teaser of what we'll see later on in this chapter. So let's try to get a few more atom counts in the chat, and then we'll discuss in about 1 minute. Okay, so let's discuss. So remember, the subscript applies to everything in the parentheses. So we have 2 nitrogens, 8 hydrogens, 2 chromiums, and 7 oxygens. This NH4 unit is known as ammonium, while Cr2O7 2- is known as dichromate. just for those who are curious. For the following example, we have 3 magnesium atoms, 2 phosphorus atoms, and 8 oxygen atoms. So the polyatomic ion PO4 3- is known as phosphate. So we've completed our atom count and we've identified our polyatomic ions. So we're comfortable reading chemical formulas. Any questions on this example? Any questions on this example? Okay, so let's keep going now. When we're talking about predicting the formulas of ionic compounds, we have to work on the following premises. So stable, isolable, solid ionic compounds are neutral. They have a total charge of 0. The total charge of an ionic compound is the sum of the total charge of each ion in that compound. So we can add up the charge of our cations and add up the charges of our anions. And for an ionic compound that is isolable, that is neutral, it will have a total charge of 0. Okay, so how do we figure out the formula of an ionic compound? Well, first we determine the charge of each component ion. So you can figure out the charges of most ions using periodic trends. Just as a refresher, remember that metals prefer to form a charge equal to their group number. Classic example would be calcium, which is a 2A element, forming calcium 2+. Conversely, our nonmetals adopt a charge equal to their group number -8. So for example, chlorine, which is a 7A element, forms chloride, Cl-. Another way that you determine the charge is that you need to know the common charges of the polyatomic ions from the table I've provided you. If you don't know the charge for a polyatomic ion, you're somewhat stuck. So, the last major way that you can determine the charge is that names involving metal ions include the metal cation charge. So for example, iron 2 bromide would be Fe2+, where the charge is indicated in Roman numerals. So, once we figure out the charge of each component ion, what you can do is you place the charge of each ion in the subscript for the opposite ion. So looking at our iron 2 bromide example, we have Fe2+, and if we think about bromine, which is a 7A element, bromine would prefer to adopt a charge of -1, which would be bromide. So now that we have each of our charges in place, all we have to do is we place the charge of each ion into the subscript of the opposite ion. We quote unquote cross our charges. So that would give us a predicted formula of Fe1Br2, which would just give us FeBr2. Now we can verify that this method and shortcut works. So we're going to verify that the total charge of the ions match the total charge of the ionic compound. So for example, if we're looking at iron 2 bromide, we will look at our total charge, which is the charge of our cation, which is iron, is +2. We have one iron atom, one iron ion. The charge of our anion is -1, and our number of anions is 2. That in turn gives us a total charge of 0. Does this example make sense to everyone?
Yes, and that's to the iron and bromine,
Yes.
right up there? Okay.
Yeah. So our total charge equals 0 by adding up the charge of iron and bromine times the number of atoms in our final formula. So as we see, our total charge does equal 0 as expected. So let's keep going now, and let's do another representative example where we're asked to write the formula of a compound containing iron 2+ and sulfur 2- ions. So we have, Fe3+ and S2-. So we write out each of our charges, and then we cross our charges. That in turn gives us the formula of Fe2S3. Does this example make sense to everyone? Figuring out the formula given the ion charges?
So when it's S2 negative and we cross it over, it makes it positive?
Yes, so you never write a negative value for the subscript, you just take the number for the charge.
Oh, okay, got it.
Does that make sense?
Yes.
Perfect. So let's try, and I'd like you to work on this next example where it's asking barium oxide is composed of barium and oxygen ions, and I'd like you to write the chemical formula of barium oxide. And there's one other rule that comes into play for these types of formulas, is that the ratio of atoms should be the simplest whole number ratio. So for example, a 3:3 ratio would just be simplified to a 1:1 ratio. You want the simplest possible ratio of atoms in your formula. So let's work on this example. Let's give everyone about 2 to 3 minutes to write the proposed formula for barium oxide after figuring out the charge, and then we'll discuss this example in about another 2 to 3 minutes. We're already seeing some reasonable responses in the chat, but don't be shy to share your other responses in the chat, and I'd be happy to provide feedback. And we'll discuss this example in another minute. Okay, so let's discuss. So barium is a metal. It's a group 2A metal. So what charge will barium adopt? What charge will barium adopt?
2 plus.
Yep, exactly right. Oxygen as a 6A nonmetal will adopt a charge of 2 minus, because 6 minus 8 is -2. Now that we have our two charges in place, we cross our charges, and that in turn gives us Ba2O2. But we're not done. We should have the simplest whole number ratio of atoms. So rather than 2 to 2, we'll simplify it to 1 to 1. And that gives us barium oxide as our chemical formula. Does that make sense to everyone? Any questions on this example? If not, let's work on another pair of examples. Let's work on another pair of examples. And for this second example, I'd like you to try to remember your fixed charge transition metals. We discussed this earlier on in the notes, and I just want you to remember that silver prefers to form silver plus. So let's work on these two examples. Let's try to write the proposed formulas for each of these two compounds, and then we'll discuss these examples in about 3 to 4 minutes. And we're starting to see some reasonable responses in the chat, but don't be shy to contribute your own responses, because the more responses we have, the more effectively I'm able to provide feedback and design follow-up examples. And we'll discuss this example in another 1.5 to 2 minutes. And again, don't be shy to share your responses in the chat, and I'd be happy to provide feedback. Okay, so let's discuss this example. So in the first case, we're looking at aluminum nitride. So we write out each of our charges. We cross our charges. That gives us our preliminary formula. And then we write the simplest ratio of atoms, which in this case would be just AlN for aluminum nitride. Silver phosphide is composed of silver ions and phosphorus ions. Remember, I mentioned the fixed charge transition metals, and you're going to need to have those memorized and be familiar with them for problems such as this. Silver is pretty common in compounds that we'll handle in this class and that we'll name in this class. So we take our charges. Silver is silver plus. Phosphorus is a 5A element. 5 minus 8 gives us -3. So phosphorus adopts a 3 minus charge. We cross our charges. That in turn gives us Ag3P, or silver phosphide. Does this example make sense to everyone? Any questions on this example? If not, let's continue on and let's deal with some polyatomic ions. Lithium carbonate contains lithium and carbonate ions, while zinc phosphate is composed of zinc ions and phosphate ions. Now, before I let you loose on this problem, what charge does zinc prefer to adopt? What charge does zinc prefer to adopt? +2, it's a fixed charge transition metal. It's important that we're familiar with our fixed charge transition metals as they pop up in many very common compounds. So I'd like you to work on these two problems and write the formulas for these two compounds, and then we'll discuss in about 3 to 4 minutes. Remember, you'll need your polyatomic ion table to know the formula and charge of your polyatomic ions. And we're already seeing some reasonable responses in the chat. And remember, when you cross the charges, the charge goes to the opposite atom or polyatomic ion. So we're starting to see some reasonable responses in the chat, and we'll discuss in about another 1.5 to 2 minutes. And remember to be very careful with the charge of carbonate and phosphate. And we'll discuss this example in about another minute. So let's talk about this example. So lithium carbonate is composed of lithium ions. Lithium is a 1A element, so it's lithium plus. Carbonate is CO3 2 minus. We write out each of our ions, and then we cross the charges, and that gives us Li2CO3 for lithium carbonate. Does this first example make sense to everyone? Does this first example make sense? Let's look at this second example for zinc phosphate. So zinc adopts a 2+ charge in most ionic compounds. Phosphate is PO4 3-. So writing out the formula for zinc phosphate, we cross our charges, remembering that the subscript applies to all atoms in our parentheses, and that gives us zinc 3PO4 2. And it's really important that you put the phosphate in parentheses because we have 2 phosphate ions. Does this example make sense to everyone? Any questions on these examples? If not, let's work on another set of examples. I'd like you to write the formula for ammonium chloride and scandium bromide, where scandium prefers to adopt a 3+ charge as it is a 3B transition metal, and it's an exception to the variable charge transition metals. It's another one of our fixed charge transition metals. And don't be shy to share your responses in the chat, and we'll discuss these examples in about 3 minutes. We're starting to see some reasonable responses in the chat. Don't be shy to share your additional responses, and then we'll discuss momentarily. Keep in mind that ammonium is the name of a polyatomic ion of the form NH4+. and we'll discuss this example in another minute. Really don't be shy to share your responses, as the more responses I see, the more effectively I'm able to provide feedback and design follow-up examples. Okay, so let's discuss. So ammonium chloride. So we draw out ammonium, which is NH4 plus. Chloride is Cl minus. We cross our charges. We get a 1-to-1 ratio, which gives us the formula NH4Cl. Does this example make sense to everyone so far? Any questions so far? Next, we're going to look at scandium bromide, where we have scandium 3 plus. And then for bromide, bromine is a 7A element, so it prefers to adopt a charge of -1. Writing out scandium and bromine, we cross our charges. That gives us SCBr3, or scandium bromide. Does this example make sense to everyone? Any questions on this example?
Professor, can you go over the bromine? It's a 7A,
Yep.
and how
Yep.
we end up with only.
So for nonmetals, the charge is equal to the group number -8. And 7 minus 8 gives us a predicted charge of -1.
Got it. Thank you.
Perfect. So these examples were carefully designed to cover most cation and anion charge combinations, and these can serve as general solutions for a lot of formula problems. Why does that work? Well, the process and the formula that we use to calculate the number of each cation and anion only really cares about the charge of each cation and anion. In other words, you can replace any ion in an ionic compound with another ion with the same charge and get a new valid chemical formula. So to show you an example of this, if you have sodium plus and Cl minus and you cross your charges to get sodium chloride, we can just as easily replace sodium with potassium because it has the same charge. And we would get a very similar formula. Now, we can take this one step further and even start performing substitutions when we have polyatomic ions. So let's look at an example of aluminum oxide. Aluminum oxide is composed of aluminum and oxygen ions. Aluminum is a 3A metal, so it prefers to form aluminum 3 plus. Oxygen is a 6A nonmetal, so it prefers to form oxygen 2 minus. We take aluminum 3 plus and oxygen 2 minus and we cross our charges and we get Al2O3. Now, what's really interesting to consider is we can just as easily replace aluminum 3 plus with any cation with a 3 plus charge and replace oxygen 2 minus with any anion with a 2 minus charge. Now, why is this important? This allows us to quickly write the formula of ionic compounds by analogy. So let's showcase an application of this. I'd like you to predict the formula of the ionic compound generated from iron 3 plus and SO4 2 minus. So we have iron 3 plus and SO4 2 minus. What would the formula be? What would the formula be for this compound if we cross our charges? we'd get Fe2SO4 3. Perfect. Does everyone notice how these two formulas have very similar subscripts, how the subscripts are almost identical? Or in fact, they are identical for that matter. Does everyone see how if you have the same cation and anion charge, your general formula will be the same? You'll have the same ratio of ions. Does everyone see that? Does that make sense to everyone? Does everyone see the connection between the charge and our formula? So essentially, if you've solved one example for a given cation and anion charge, you've solved all of the examples because the problem-solving process is going to be exactly the same and the general formula is going to be exactly the same. So that's why I strategically chose the examples that we covered to address most of the common cation and anion charge combinations. Pretty useful when you start thinking about things in a general sense. So let's take a look at the following two examples. I'll give everyone about 3 to 4 minutes, and I'd like you to write the formula for iron 2 cyanide and for tin 4 sulfate. Remember, the charge can be indicated using a Roman numeral, where this 2 indicates +2 and this 4 indicates +4. So let's work through this example and then we'll discuss momentarily.
Professor, what's the element for cyanide? What letter represents?
Cyanide, it's not an element, it's a polyatomic ion. Just like sulfate, these are polyatomic. And so you'll use the table to write the formula.
Oh, okay. I don't have a table in front of me.
It's in the note set. Cyanide, for those who are curious, has the formula Cn minus.
Cn minus?
Yes.
Thank you.
Would someone like to help us out for sulfate? Would someone like to tell us what is the formula and charge of sulfate? Reading through our table of polyatomic ions from our note set.
Is SO2 minus?
Yep,
Sulfate?
SO4 2 minus, exactly right. Perfect. And eventually, by the time we reach our exam, you'll have all of these polyatomic ions memorized, and these examples are designed to help integrate the naming and writing of formulas of polyatomic ions in the problem-solving process. So let's keep going and let's try to write out the formulas of these two compounds. Don't be shy to share your responses in the chat, and don't be shy if your response is different compared to your classmates. The more responses that we are able to see, the more I can provide feedback and address any concerns that you have. And we'll discuss these examples in about another minute. Okay, so let's discuss. So for iron 2 cyanide, we have Fe2 plus. Cyanide, we have Cn minus. We cross our charges, and that gives us FeCN2. Any questions on this first example? Any questions on this first example? Okay, let's look at tin for sulfate. Let's look at tin for sulfate now. Tin 4, so we have tin 4 plus. Sulfate is SO4 2 minus. We cross our charges. That gives us SN2 SO4 4. We can simplify our charges to SN SO4 2. There we go. Does this example make sense to everyone? Any questions on this example? Remember, you want the simplest ratio of ions in your final formula. Any questions before we move on to the next set of examples?
How do we simplify just 2 minus 4?
So it's not 2 minus 4, but you take 4 divided by 2, and that gives you a 2-to-1 ratio.
Got it. Thank you.
You want the simplest whole number ratio. So no fractions, but the simplest whole number ratio. Does that make sense?
Yes, thank you.
Perfect. So let's keep going now, and let's look at the following example. I'd like you to write the formula for lead 4 acetate, remember 4 plus 4, and cadmium nitrate. So you're going to need to know your polyatomic ions to answer these questions. You can use your table of polyatomic ions, and this is a good way of studying and integrating the polyatomic ion names and formulas, because quite simply, the act of using a name and formula to solve a problem improves your retention of that name and formula. One issue that we do have to address, would someone like to volunteer and tell us the charge of cadmium? Cadmium, that's a transition metal. How do we know the charge? It's fixed, so it's 2 plus. It's another one of our fixed charge transition metals. So let's work on these examples for about 3 minutes, and let's try writing the formulas for these compounds, and then we'll discuss momentarily. And don't be shy to submit the proposed formulas in the chat. and we'll discuss this example in about 1.5 to 2 minutes. Let's try to get a few more responses in the chat before we discuss in about 1 minute. And really don't be shy to submit your responses. And even if they're different from your classmates, and even if they aren't correct, it allows me to understand what problem-solving process you're utilizing, and it allows me to provide more directed feedback. Okay, so let's discuss this example. So lead 4, it's lead 4 plus. Acetate has the formula of CH3CO2 minus or C2H3O2 minus. Both are ways of writing acetate. So now that we have acetate with a charge of -1, we cross our charges, and that gives us PbCH3CO2 4. So this is the complete formula for lead 4 acetate. For cadmium nitrate, cadmium is cadmium 2 plus, nitrate is NO3 minus. We cross our charges, that gives us CdNO3 2. Does this example make sense to everyone? Does this example make sense? Any questions? If not, let's keep moving on and let's talk about predicting ion charge from the formula. Since transition metals can adopt a variable charge, the charge of the metal cation needs to be calculated. So the total charge of an ionic compound is the sum of the total charge of each ion in that compound. Now, since the total charge of a neutral ionic compound is 0, if we add up the charge of our cations and anions, we should get 0. So if we want to figure out the charge of our cation, if we want to figure out the charge of our transition metal, which can have a variable charge depending on the formula, we first need to determine the charge of the anion using periodic trends and from the common charges of polyatomic ions. So for example, we know that nitrogen as a 5A element adopts a charge of 3 minus because 5 minus 8 is -3. Likewise, if we look up a polyatomic ion like sulfate, we know sulfate has a 2 minus charge. Now, what's really cool is that once we have the charge of our anion, we can solve for the charge of our cation. This method is completely necessary when you're trying to figure out the charge of a transition metal, because we need to know the charge of our transition metal in order to name it. So for example, what is the charge of tin in SnCl4? Well, we know that for chlorine as a 7A element, chlorine adopts a charge of -1. So then, if we're solving for the charge of 10, we take -1 times the charge of our anion, which is -1, times the number of our anion. And how many chloride ions do we have? How many chloride ions do we have? We have 4. So we multiply by 4, then we divide by the number of 10 ions. And how many 10 ions do we have? 1. So that gives us a charge for 10 of +4. And that allows us to name this compound, as we'll see later on, as 10,4-chloride. So we need to be able to figure out the charge of our transition metal in order to effectively name our transition metal. Does that make sense to everyone? Does this idea and this formula make sense? Any questions? So let's try to apply this, and I'd like you to calculate the charge of the metal cation and the anion found in the following 2 examples. So I'd like you to calculate the charge of the ion in the following 2 examples. Another trick that you can use is, suppose we were looking at our 10 chloride example. One trick is you can simply reverse cross the charges, and that would tell us we have a charge of +4 for 10 and -1 for chloride. And all we have to do is just check that the charge matches our periodic trends. So, given the formula of each of these ionic compounds, I'd like you to tell me the charge of the indicated cation or anion. And we'll discuss this example in about 4 minutes. So let's try to calculate the charge of each of our cation and anions in these 2 examples. And the charge should indicate whether it's a cation or anion, and you should indicate the magnitude of the charge, whether it's +1, +2, +3, etc. Remember, most metals have a positive charge, while most nonmetals have a negative charge. And we'll discuss this example in about another 2 to 3 minutes. And we'll discuss this example in another minute. Okay, so let's discuss this example. So let's use the reverse cross method first. So if we reverse cross our charges, we get vanadium 5+ and ClO2 minus, which matches our predictions and matches the known charge of chlorite. Another method we can do is we can use our formula. The charge of vanadium is equal to -1 times the charge of our anion, which is -1 because this is chlorite. We have 5 chlorite ions, and then we divide by the number of vanadium ions, and that gives us a charge of vanadium as 5+. Perfect. So does this first example make sense? Does this first example make sense? Okay, so in this next case, we have Al2X3. So if we reverse cross our charges, we get Al3+ and X2-. And just to make sure, aluminum does in fact adopt a 3+ charge, so all is right with the world. If we wanted to solve for the charge of X, we take -1 times the charge of our cation, which is +3, times the number, which is 2, over the number of anion, which is 3, and that gives us a charge of -2. Any questions on this example? Any questions on this example? If not, let's identify the charge of the ions in these two compounds. So I'd like you to work on these two examples over 3 minutes, and then we'll discuss these examples as a group. So I'd like you to assign the charge of each of the ions in these following compounds, and then we'll discuss in about 3 minutes. Practice really does make perfect for these problems and these methods. And we're already seeing some reasonable responses in the chat. If you have any questions or if you have a proposed response, don't be shy to submit your questions and responses in the chat, or to ask any questions or propose your responses in this discussion verbally. And I'd be happy to address any of your questions and provide feedback. And we'll discuss in about 1 more minute. Okay, so thank you for everyone who contributed their responses in the chat. So looking at titanium nitride, we know nitrite has a -1 charge. If we reverse cross our charges, we get titanium SO4 plus and NO2 minus. This in turn matches our predicted charge for nitrite. Does this example make sense to everyone? Does this example make sense? Any questions? Looking at the next example where we have a compound containing magnesium and an anion X, if we reverse cross our charges, we get magnesium 2 plus and X minus. And that matches our indicated and known charge for magnesium. Do these examples make sense to everyone so far? Any questions before we look at another set of examples? Okay. So we've already talked about the reverse crossing method. And let's try to apply and let's try to assign the charge of each of our cations and anions in the next 3 examples. The reason why we're doing so much practice on this specific type of problem is because identifying the charge is not only important for naming compounds, but it'll be important when we start writing out equations. So we'll work on these examples over the next 3 minutes, and then we'll discuss. And if you have any questions or if you'd like to submit your proposed responses, don't be shy to use the chat or to propose your responses and questions verbally. And we discuss these examples in about 3 minutes. And again, don't be shy to share your responses in the chat, and we'll discuss in about another 1.5 to 2 minutes. And we're already seeing some reasonable responses in the chat, and we'll discuss in about another minute. Okay, so we see a nice pool of responses in the chat. So let's discuss these examples. So for cobalt sulfate, we reverse cross our charges, and that gives us cobalt 3 plus and sulfate 2 minus. For the following scandium compound, we again reverse cross our charges, and that gives us scandium 3 plus and X minus. Finally, for nickel acetate, we write out nickel and acetate, and then we reverse cross our charges, and that gives us nickel 3 plus, and acetate has a -1 charge. Do these examples make sense to everyone so far? Is everyone comfortable with these examples so far? Perfect, perfect. So there's one other rule that you need to consider and be really careful of. If the charge of a single ion does not match the known charge for that ion, you need to multiply both of your charges by a common whole number. So for example, if we're looking at nickel dichromate, if we reverse cross our charges, we get nickel plus and dichromate minus. But we know from our polyatomic ion table that dichromate has a 2 minus charge. So then, to fix this problem, I multiply both of my charges by 2. That in turn gives me nickel 2 plus and dichromate 2 minus. And now my charges match. So nickel has a 2 plus charge and dichromate has a 2 minus charge. Does this idea make sense? Any questions on this idea? You want to make sure your assigned charges match the known charges for your common anions and polyatomic ions. So let's apply what we've learned to the following 2 examples. So I'd like you to assign the charge of X in this aluminum X compound, and I'd like you to assign the charge of copper in copper phosphate. Finally, I'd like you to assign the charge of Y in Ca2Y. So this will be the last set of examples for today, and we'll give everyone about 4 minutes to work on these examples, and then we'll come together as a group to discuss. So it's good that we have a pool of responses in the chat so far. Let's keep working on these examples and we'll discuss in about another 2 minutes. And we'll discuss this example in about 1 minute. And if there are any questions, don't be shy to ask them in the chat or verbally, and I'd be happy to provide feedback. Okay, so let's discuss. So we can cross our charges just like normal, but, and this is really key, we know that aluminum has, in reality, a 3+ charge. So then we need to multiply both of our charges by 3. That gives us aluminum 3+ and X 3-. Does this example make sense? Is everyone comfortable with this idea? Let's look at another example where we have copper phosphate. So we reverse cross our charges. That gives us Cu+ and PO4-. We know that phosphate has a 3- charge, so we multiply each of our charges by 3 to give us copper 3+. Finally, for the following compound containing calcium and this unknown Y, we reverse cross our charges. We get calcium+ and Y2-. However, we know calcium has a 2+ charge, so we multiply both of our charges by 2, giving us calcium 2+ and Y4-. Does this example make sense to everyone? Any questions on this example? So we're at the end of today's scheduled lecture period.